All right, so we're going to be starting Unit 5, Energy, which encompasses mostly Chapter 7 in your textbook. I'm going to be breaking this up into two kind of video segments. The first segment is going to cover work and power, and our second segment will cover mechanical energy, which is the idea of potential and kinetic energy, and work energy theorem and conservation of energy. So work. Work involves a force over some displacement. Now that force and that displacement need to be parallel. If the displacement and the force are at some angle, it's only the components of the force and the displacement that are parallel. Generally, the equation is nice and simple for us. It's going to be work equals force times distance, or force times displacement. And we need to realize that the work is going to change the energy of an object. Now, the unit for work is the joule, and that comes from a Newton times a meter. A Newton meter is a joule. So the force, again, has to be in the same direction as the displacement to do work. It has to be parallel. They can be kind of opposite, like one's positive, one's negative, and you get negative work, but again, they have to be parallel to do work. So, quick little check-in here. So if you push against a stationary brick wall for several minutes, you do not no work on the wall at all, both of the above or none of the above. Correct answer is on the wall, because you're not moving the wall. There's no displacement of the wall, even though you're exerting a force on the wall. All right. Your muscles do slightly contract and expand, so there is some displacement of your muscles. So there's being work done on your muscles, but the wall itself is not moving. So to get an idea of work, we can think about lifting a load or lifting a load that's twice as heavy, different distances. So twice as much work is done lifting two loads, one story, as lifting that same load, single load, the same distance. So twice the force for the same distance is more work than only one load for the same distance. Okay? So 100 newtons of force for 1 meter versus 200 newtons of force for 1 meter. You also could do it by doing more distance. So I could say I've got that 100 newtons of force, but I could go 2 meters, 2 stories. Okay, that would be twice the work. Versus I could say I've got just the 100 newtons of force for the one story, the 1 meter. That would just be, that amount of work. So work is done in lifting a barbell. How much work is done in lifting a barbell that is twice as heavy? So it requires twice the force, the same distance. Is it twice as much, half as much, the same, or it depends on the speed of the lift? Correct answer is twice as much, right? Because again, work is equal to force times distance. So if the distance stays the same, but now the force is twice the force, we would end up with twice the work. So another quick little check-in here. You do work when pushing on a cart with a constant force. If you push the cart twice as far, then the work you do is less than twice as much, more than twice as much, or 0. And again, this will be twice as much. So if we go through the idea that work is equal to force times distance, this time the force stays the same, but our distance becomes twice the distance. That gives us twice the work. So power. We're used to thinking about power when you think about things like electricity, or cars, think about horsepower. But what power really is, it's the measure of how fast work is done. So power by definition is work over time. Okay, the rate at which the work is done, how fast you can do that work. And the unit of power is basically joules per second, or what's called a watt. Think of light bulbs. We say a light bulb is so many watts, or a computer power supply is so many watts. And it's named after James Watt, who developed a steam engine. And he was trying to find a way to, sell steam engines, and that's how he also came up with the unit of the horsepower. He was trying to say how much power his steam engine could replace in horses. It just so comes out to be that 1 horsepower ends up being 746 watts. We'll occasionally use that conversion factor when we want to go between horsepower and watts, because things like cars and engines, generally we think about horsepower. Things that are electrical, like light bulbs and computers and things like that, we're used to talking about watts. So 1 joule per second is 1 watt. When it comes to your home, though, you're used to talking about kilowatts sometimes. Like you have how many kilowatts does the home use, or how many kilowatt hours when you get to the actual work done or the energy used. And 1 kilowatt is 1,000 watts, because kilo, that prefix means 10 to the 3, or 1,000. So a job can be done slowly or quickly. Both may require the same amount of work, but different amounts of energy, momentum, power, or impulse. The correct answer is power, because work is going to just change the energy. So if it's the same amount of work, same amount of energy. But how quickly or slowly it's done, the rate at which the work was done, the time it took, would basically be the power, because work over time is power. Now, another interesting thing to come out of power is the fact that we don't just have to define it as work over time. So when we think about things like cars, well, why does a car need to have so many horsepower or so much power to go down the road? It's not just about accelerating the car. It could be just about maintaining that car's speed going down the road. Think about a car going down the road against air resistance. There's a minimum speed that it's going to go and minimum force it has to do to go against that air resistance. So we can think of work as being force times distance. Okay? And if I do force times distance over time, I can then regroup the distance and the time together and say force times distance over time. But we know distance over time is the definition of average velocity. So the other way to define power is the force required times the average velocity that that vehicle or that object is moving with because of power.